बिस्मिल्लाहिर्रहमानिर्रहीम अस्सलामु अलैकुम। कैसे हैं आप? दिस इज़ लेक्चर नंबर 16। लेट्स स्टार्ट। First we take a review of last lecture. In last lecture we discussed the concept of movements, and in particular we discussed movements about mean, which are also called central movements, and we also discussed movements about any arbitrary origin, and then we discussed movements about zero. And we also did the related Excel demos, how to calculate movements for the grouped data and for the ungrouped data. And we also did Excel demos of calculating central movements or movements about mean, and the demos in Excel of calculating movements about origin. So now let us discuss the objectives of the current lecture. In this lecture we are going to discuss the relation between central movements and the movements about origin. This means that we are going to discuss that how we can calculate the central movements or the mean movements with the help of movements about origin. And then we will discuss one very important concept, which is called movement ratios, and then we will also discuss skewness and kurtosis as well. Let's start. So conversion from movements about mean to movements about origin. So sample movements about mean in terms of movements about origin can be given by this formula. So it is mr, which is the rth central movement. This is equal to rc0 m dash r minus rc1 m dash r minus 1 into m dash 1 plus rc2 m dash r minus 2 into m1 dash whole square plus so on, minus 1 raised to power r m1 dash power r. So here this rc0 rc1, this is used for combinations, so we can write it as ncr. So this is equal to ncr. We can write it in both ways, either using this notation n then cr, so and then this ncr. So this is equal to n factorial over r factorial into n minus r whole factorial. So this combination mean we are selecting r objects or r items out of n items. So in how many ways we can select r items out of n items? So it is n factorial over r factorial into n minus r whole factorial. We will also discuss this combination rule in detail in our next lecture. So where this n factorial is, it is n into n minus 1 into n minus 2 and so on, 3 to 1. So suppose we are interested in calculating 4 factorial. So by using this formula it will be 4, then 4 minus 1 3, 4 minus 2 2, and then 4 minus 3 1. So we have to go up to 1. So 4 into 3 12, 12 to 24 into 1 24. So 4 factorial is actually the number 24. So similarly if we have 5 factorial, so we can write it as 5, then 5 minus 1 4, 3 2 1. So it is 5 into 4 20 into 3 60 into 2 120 into 1, so 120. So 5 factorial is 120. And note that we can also write this 5 factorial as 5 into this 4 3 2 1. It is actually what? It is 4 factorial. So we can write this 5 factorial as 5 into 4 factorial. So this 5 into 4 factorial. So there are several ways in which we can write the factorial. So there is one important rule to note, that 1 factorial is 1 and 0 factorial is also it is 1. So these are two very important rules. So coming back to our main formula, so mr, which is the rth central sample movement, it is RC0 m dash r, then minus sign RC1 m dash r minus 1. Look at here, we have 1 here, so subtract this 1 from r minus 1, and then m1 dash raised to power 1, and then RC2, so subtract 2 minus r minus 2, and then m1 dash, this is m1, so m1 dash whole square. So here we have number 2, so take square of m1 dash and then subtract this number 2 from this r. And similarly, if we proceed in the same way, the last term will be minus 1 raised to power r into m1 dash raised to power r, and here we have RCR as well. So RC0, so start from 0, then RC1, RC2, RC3 and RCR, and then we have here we have m1 dash raised to power 0, so any number raised to power 0 is 1, so that's why I have not written here. So then m1 dash raised to power 1, then m1 dash raised to power 2, and so on, m1 dash raised to power r. So next, note that the first term has plus sign, the second term has minus sign, the third term has again plus sign. So in order to cover it, so I have written minus 1 raised to power r. So if r is an even number, for example minus 1 raised to power 1, so it will be minus 1. So here we have r1, so 1 is an odd number, so in case of odd number we will get minus, but in case of an even number, 2 is an even number, so it will give us plus sign. So here we have 2, which is even number, so we are getting plus sign. So here we have 0, so minus 1 raised to power 0. So remember that anything raised to power 0 is always equal to 1. So that's why it is 1 with plus sign. So this is how we can get the earth central movement from the movements about origin. So this is one very important formula which I will use in order to calculate earth sample movement about mean, earth movement about mean in terms of movements about origin. So currently I am using I have written the formula only for sample movements, and then using the same rule we can write the formula using population movements, which I will explain after covering this sample movements. So if we replace this r in this formula by 1, so we get first sample movement about mean in terms of movements about origin. So just replace by r by 1 in this formula. So replacing r by 1, we get m1, and here rc0, so it means 1c0, and m dash r, so m dash 1, because r is replaced with 1, and there is no need to write this expression m1 dash raised to power 0, because anything raised to power 0 is 1, and then put minus sign, then r minus 1, so replace r by 1, so 1c1, and then m dash 1 minus 1, which is 0, so there is no 0 movement, so it is, we will skip it, and then m1 dash raised to power 1, this one as it is. So now we have to calculate this 1c0 and 1c1. So just replace this n by 1 and this r by 0, so and use this formula. We will using this formula we can calculate this 1c0. So suppose we are interested in calculating this, so using this formula we will write 1 factorial. So here we have n factorial, so n in this case is 1, so it means it is 1 factorial, and then in the denominator we have r factorial, which is 0 factorial, into n minus r, which is 1 minus 0 whole factorial. So note that 1 factorial is 1, this 0 factorial is also 1, and 1 minus 0 is 1 factorial. 1 factorial is also 1. So this dot is used for multiplication. So 1 into 1, 1. So 1 over 1 we get 1. So it means 1C0 is 1. So replacing this full expression by 1, so 1 multiplied with m1 dash, we get this m1 dash here. And then put negative sign as it is, 1C1. In order to calculate this 1C1, so again use the same formula. It will be 1 factorial, 1 factorial, 1 minus 1 whole factorial. So 1 factorial is 1, this 1 factorial is again 1, 1 minus 1 which is 0 factorial, which is also 1. So 1 over 1 we again get 1. So this is also 1, so we get m1 dash. So m1 dash minus m1 dash we get 0. So it means the first sample moment about mean is 0. So similarly we can use the same formula. So there is slight correction here. So we have m1 square and then rest of the formula is fine. So in order to calculate the second sample moment about mean in terms of moments about origin, so just replace this r by 2. So replacing r by 2, so we get m2. So here 2c0, then m2 dash, this one as it is, then minus as it is 2c1, then m dash 2 minus 1, it is 1, and this m1 dash as it is, then 2c2, then m dash 2 minus 2 which is 0, so no need to write it, but here we have m dash 1 square, so this is m1 dash whole square. So now we have to simplify this 2c0, 2c1 and 2c2. So again we can calculate 2c0, so 2c0 is 1, so we get m2 dash, this minus sign as it is, so 2c1 is 2, and then this m1 dash both are being multiplied, we get m1 dash whole square, then this 2c2 it is 1, and we have m1 dash whole square, so this m1 dash whole square as it is, this one m1 dash whole square. So here we have minus 2 m1 dash whole square plus 1 times m1 dash whole square. So both terms are same, their coefficients are different, so we can combine these two terms. So second term, its coefficient is minus 2, while the coefficient of third term is plus 1, so minus 2 plus 1 we get minus 1. So this is simplified to m2 dash minus 1 time m1 dash whole square. So it means if we know the values of second moments about origin and the first sample moment about origin, we can use this formula to calculate the second sample moment about mean. So this is the relationship between second sample moment about mean and the moments about origin, the second moment about origin and the first moment about origin. So similarly, if we replace r by 3 in this formula, so we can get the third sample moment about mean in terms of moments about origin. So remember that this is m1 dash whole square. So just replacing r by 3, so we get m3, so 3c0, m3 dash, then 3c1, m dash 3 minus 1 we get 2, this m1 dash whole as it is, then 3c2, so we get 3 minus 2 which is 1, so it is 1, and m1 dash whole square, and last one is 3c3, so it will be m1 dash whole cube. So remember that this is very important to note that the signs, they are alternate. It means the first sign is plus, second one minus, third plus, fourth one must be minus. So next 3c0 it is 1, so m3 dash, then 3c1 it is 3, so minus as it is 3 times m2 dash, m1 dash. Then 3c2, it is again 3, and we have m1 dash. This one is m1 dash as it is, and we have m1 dash whole square. So this one is also as it is. So 3c3, it is 1, so minus as it is, and here we have m1 dash whole cube. So this is m1 dash whole cube. So in next step, write the first two terms as it is, and here we have 3 times m1 dash and then m1 dash whole square. So it means we can combine these two terms, so it will be m1 dash whole cube. And here we have m1 dash whole cube, this one as it is. So now look at the third and fourth term. Both terms are same and their coefficients are plus 3 and minus 1. So we can combine these two terms. So plus 3 minus 2, we get plus 2 times m1 dash whole cube. So this is m1 dash whole cube. So this is the formula. If we know the values of these moments, sample moments about origin, m3 dash, m2 dash, m1 dash. So using this formula we can calculate m3, which is the third sample moment or third central moment or third sample moment about mean. So similarly, if we replace r by 4, we can get fourth sample moment about mean in terms of moment about origin. So note that this is m1 dash square. So replacing this r by 4, we get m4, then rc0, 4c0, m4 dash, then rc1, 4c1. This 4 minus 1 we get 3, then 4c2, this 4 minus 2 we get 2, and here we have m1 raised to power 2, then 4c3, r minus 3, 4 minus 3 we get 1, and this one cube, and then in the end we have m1 raised to power 4. So remember that m1 raised to power 1 square, then cube, then r. So here same result, m1 raised to power 1, m1 dash whole square, m1 dash whole cube, m1 dash whole 4. So there is slight correction. So 4c0 is 1, so we get m dash 4, 4c1 is 4, m3 dash, m1 dash as it is, then 4c2 is 6, m2 dash, m1 dash whole square, then 4c3 it is 4, m1 dash, and this one is also m1 dash whole cube, then 4c4 it is 1, and we are left with m1 dash raised to power 4. So in next step, write first term as it is, second term as it is. So here we have 6 m2 dash, m1 dash whole square. So this is m1 dash whole square, and we have this m2 dash as it is, and then we can combine these two terms. So minus 4 m1 dash and this m1 dash cube. So 1 dash raised to power 1 and cube, we get m1 dash raised to power 4, and here we have m1 dash raised to power 4 as it is. So again we can write this term as it is m1 dash, this one, and we also have m2 dash, and minus 4 plus 1 we get minus 3 m1 dash raised to power 4. So it means, so just let me write here in a more proper way. So it is 4 times m3 dash m1 dash plus 6 times m2 dash m1 dash whole square minus 3 times m1 dash whole raised to power 4. So it means if we know the values of these sample moments about origin, m4 dash, m3 dash, m2 dash, m1 dash, so using this relation we can calculate the fourth sample moment about mean, or fourth central sample moment. So let me express these results in the form of a summary. So sample moments about mean in terms of moments about origin. So m1 is equal to m1 dash minus m1 dash, which is 0, m2 is given by this result, and m3, and here we have m4. So this is the simplified form. So similarly, we can calculate population moments about mean in terms of moments about origin. So in case of population movements, the relations are the same, so we have to just replace the sample movements with the population movements. So m1, m2, instead of m1, m2, we will write mu1, mu2, mu3, mu4. So instead of m1 dash, so we will write mu1 dash and mu2 dash, 3 dash, and rest of the formulas, these formulas, they are exactly the same. So only there is notational difference. So for sample moments we use m, for population units we use mu. So using these formulas we can calculate moments about mean from the moments about origin. Suppose in a question you are provided with the values of m1 dash, m1 dash, m2 dash, m3 dash, and m4 dash. So suppose you know their values m1, m2, m3, and m4 dash. So from these four moments, question is calculate m1. So then calculate m2, m3, and m4. So if we know these values, we can substitute these values in these formulas, and we can calculate all these sample moments about mean. Similarly, if we know the values of mu1 dash, mu2 dash, 3 dash, and mu4 dash, we can calculate population moments about mean, which are mu1, mu2, mu3, mu4, using these formulas. So now come to the moment ratios. So ratios involving moments, they are called moment ratios. The most common moment ratios are defined as, these are two in numbers. First one is called beta 1, which is mu3 square divided by mu2 cube, and the second moment ratio is beta 2, which is mu4 divided by mu2 square. And note that here mu2 and mu3, mu4, they are the population moments about mean. So using the population moments, ratios of population moments, we can calculate moment ratios. So beta 1 is the ratio of square of third population moment and the cube of second population moment. So beta 2 is the ratio of fourth population moment and square of second population moments. And one very important point to note, that since these are ratios, so hence they have no unit. So now there are some important points which are to be noted related to these moment ratios. So for symmetric distributions, equally spread distributions, just like the bell curve or the uniform distribution or the triangular distribution, so beta 1, which is the first moment ratio, it is always equal to 0. So it is used as a measure of skewness. So if it is 0, it means the distribution has 0 skewness. 0 skewness means it is symmetric. So this bell-shaped curve, it is symmetric, equally spreaded, 50% on left of this middle line and 50% on right side of the middle line. So it means if we calculate this beta 1, it will be 0. So it means it is a symmetric distribution. So similarly, beta 2 is used to explain the shape of the curve, and it is measure of peakedness. So whether the peak is above this normal curve or it is below this normal curve. So if we take this middle line as the exactly bell-shaped curve, so we can check whether this peak is above this normal curve or it is below this normal curve. So beta 2 is used to explain the shape of the curve, and it is measure of peakedness. So for normal distribution, which is a bell-shaped curve, so beta 2 is always equal to 3. So now we can also define these movement ratios for sample data as well. So movement ratios for sample data are, instead of beta 1 and beta 2, we will use B1 and B2, and instead of population movements, just replace them with their sample movements. So mu3 square our mu2 cube. So here in case of B1, so B1 is equal to m3 square our m2 cube, and similarly B2, which is second movement ratio in case of sample data, it is m4 our m2 square. So next we discuss one very important concept, which is the concept of standardized variable. So it is often convenient to work with variables where the mean is 0 and the standard deviation is 1. So suppose x is a random variable with mean mu and standard deviation sigma, so then we can define a second random variable z such that z will have a mean of 0 and standard deviation of 1 by using this relation. So z is equal to x minus mu. So subtracting mean, so it means we are subtracting this mean of x from each observation of x. So in other words, we are shifting the mean to 0, and then divide this full expression x minus mu divided by sigma. So it means we are scaling this variable with respect to standard deviation sigma. So if we divide the variable by sigma, so it means we are changing the standard deviation to 1. So this z, it is x minus mu over sigma, so it means now the mean of this random variable z will be 0, so and its standard deviation will be 1. So we can say that x has been standardized, or that z is a standard random variable. So suppose we have here x certain values, and suppose mean of x is let's say 3. So if we subtract 3 from each of these x values, so and if we take the mean of this new variable, this one, so its mean of all these entries, sum of these observations divided by total number of observations, this will be 0, because we have adjusted these observations with respect to mean. And similarly, if we divide, if suppose this random variable x with certain values, suppose it has standard deviation let's say 2. So if we divide this x by this sigma, or x by 2, actually x by 2, so it means divide each observation by 2. If we calculate the standard deviation of this these new observations, so this will be 1. So it means we have adjusted the observations with respect to their standard deviations. So and if we subtract mean as well as we divide by sigma, so which is 2, so this new variable, if I call it as z, so the new observations, if we calculate mean of all these observations, so mean will be 0 now, and if we calculate sigma, so sigma will be 1. So this new variable z, it is called standard random variable, or we can also say that this x has been standardized. So standard variable mean is 0 and standard deviation is 1. This is one very important point to note. And in real life data, most of the time we are interested in working with variables which are standardized in nature. So in practice, if we have a data set and we want to standardize it, so it means we first compute the sample mean and the standard deviation, and then for each data point we subtract the mean and divide by the standard deviation to get a new variable z, which is a standardized random variable. So this concept is very important, and we are going to use this concept in our next slide. So now we can also express the movement ratios in terms of standardized variable. So here the first movement ratio is beta 1, it is mu3 square over mu2 cube, and remember that mu3 is the third population movement about mean, so it is 1 over n into summation xi minus mu whole cube, where I ranges from 1 to n, and whole square mean, just take square of this full expression, and then we have to divide this full expression with mu2 cube. So mu2 is the second central movement about second central population movement, second population movement about mean. So it is second central movement related to population data. So it is 1 over n into summation xi minus mu whole square, and we have to take cube of it, so take cube. And in next step, write the numerator as it is, and as far as this denominator is concerned, we know that this is sigma square, so which is called the variance. So write this expression as sigma square and this cube as it is. And in next step, this 2 sigma square whole cube, we can write it as sigma cube whole square. So it is actually 2 3 the 6 sigma 6. So just writing using some trick, I have written it as sigma cube whole square. And in next step, since here we have square, here we have square, so square of numerator, square in denominator, so we can write it as whole square, and we can divide this expression by this. So in next step, since we have cube here, this sigma is a constant, so cube here, so we can divide this sigma by each element of x minus mu. So just shift this sigma here and put this cube of this whole expression. And remember that this x minus mu over sigma, it is z. So x minus mu over sigma is z, which is a standardized variable. So just replacing this x minus mu over sigma by this z. So we get 1 over n as it is, summation 1 to n, this z cube and whole square. So look at this expression 1 over n summation z cube, it is the third moment. So hence we can say that this beta 1 is the square of the third population moment expressed in standard unit. So this z is z cube, so it means we have summation z cube over n, so this means we have third population moment. Since z has been standardized, so we can say that it is third population moment expressed in standard unit, and beta 1 is the square of this third population moment which is expressed in standard units. So we will use this result in our later slides. So this is one very important result. So similarly, we can express the second movement ratio in terms of standardized variable as well. So note that the second movement ratio is mu4 over mu2 square. So mu4 is the fourth population movement, so and here we have the second population movement and whole square. And again this expression is the variance sigma square whole square as it is, write numerator as it is, and this is 2 to the 4, and we can shift this sigma, we can divide this x minus mu by sigma, so x minus mu by sigma whole raised to power 4, and this full expression is again this z, x minus mu over sigma. So it means the second movement ratio, it is actually the fourth population movement expressed in standardized unit. Again, this is one very important result, and we will use this result in our coming slides. So next we discuss one very important concept, which is the concept of skewness. So a distribution in which the values equidistant from the mean have equal frequencies is called a symmetric distribution. So any departure from symmetry is called skewness. So let us consider here a distribution which is the uniform distribution. So this is the uniform distribution. So here is the mean. So here we have the mean of this distribution. So observations which are equidistant from mean, so let us consider this observation. So it is, let's say, x1, and here we have x2. So if we measure this gap, so a gap of this first observation x1 from mean and gap of this second observation from mean, if this gap is same as this, so it is equidistance from mean if they have equal frequencies. So we can measure the frequency from the height. So suppose the frequency of each of these two values is same, which is 0.1 or 10%. So it is called symmetric distribution. Similarly, if we have this bell-shaped curve, so this is the mean, here we have mean. So if suppose we have here one point x1, here we have another point x2. So if this these observations x1 and x2, they are equidistant from mean, and this area is they have the equal frequency, then this distribution is called symmetric. And we can see from this diagram that this area is, or this frequency is same as the second one. So any departure from symmetry is called skewness. For example, we have this right skewed curve, so and we also have the left skewed curve, where right tail, if right tail is longer than the left tail, then it is called right skewed. If left tail is longer than the right tail, then we have the left skewed distribution. So now there are certain rules. In a perfectly symmetric distributions, mean is same as median, which is same as mode. So mean, median and mode, they coincide, and the two tails of the distributions are equal in length from the mean. So we can see that this here, this right tail, this one, and this one is the left tail, they are equal in length. So these values are pulled apart from the distribution. These values are pulled apart when the distribution departs from symmetry. So if distribution is not symmetric, as in this case, so you can see that right tail is longer than the left tail, or left tail can be longer than the right tail, and consequently one tail become longer than the other, as in this case. So if right tail is longer than the left tail, then the distribution is said to have positive skewness. In this case, mean will be greater than median, which will be greater than mode. And if left tail is longer than the right tail, then the distribution is said to have negative skewness, and in that case mean will be less than median, which will be less than the mode. So when the distribution is symmetric, the value of skewness should be 0, and according to Carl Pearson, the coefficient of skewness, or skewness, can be measured as skewness is equal to mean minus mode over standard deviation. But since in some cases mode does not exist, as we have discussed in our earlier lectures, so using empirical relationship, that is mode is 3 times median minus 2 times mean. So just replace this mode by this relation 3 times median minus 2 times mean here. So we can write skewness as So this SD as it is, here we have mean minus, instead of mode replace this formula, so we have 3 times median minus 2 times mean. So just open the parenthesis, so you can see that we have this SD as it is, this mean as it is, so this minus 3 times median, and this minus into minus plus 2 times mean. So 1 times mean plus 2 times mean, we get 3 times mean. So we get 3 times mean minus 3 times median whole over SD, or taking 3 common, so we get mean minus median whole divided by SD. So here we have, this one is mean minus median. So this is the general formula. So if we have the value of mean and median, so just divide this difference by the standard deviation and multiply the result with 3. So we will get the skewness. This formula is provided by Carl Pearson, and the range of skewness according to this formula is that skewness lies between minus 3 to plus 3. So most of the time the values of the skewness will be from minus 3 to plus 3. So a British statistician, Bowley, he provided another variant of the measures of skewness. So another formula provided by Bowley is known as Bowley's coefficient of skewness, which is also called quartile skewness coefficient, and this is Q3 minus Q2 minus Q2 minus Q1 whole divided by Q3 minus Q1. So it is actually the difference of quartiles. So if we simplify this formula further, we can get Q1 minus into minus, we get Q1, this minus Q2 we get minus 2 times Q2, and this Q3 as it is. I have rearranged the terms and denominator as it is, and next we know that this Q2 is actually the median. So in this formula we can write instead of Q2 we can use this alternative notation as well. So it means in order to calculate skewness using this Bowley's formula, we need to calculate the quartiles Q1, Q2 and Q3. So let us consider an example. So calculate skewness when median is 49.21 while the two quartiles are Q1 and Q3, which are also given here. So we know that this median is same as Q2. So using this formula, just replace these values here. So if you replace these values here, so Q1 is 37.15 minus 2 times median, which is 49.21 plus Q3, so Q3 is 61.27. So note that this 61 and 37, if we add up, so it is this same as minus 2 times 49.21, and here this denominator it is 61.27 minus 37.15. So we can see that in numerator we get 0. So 0 divided by anything, 61.27 minus 37.15, so we get 0. So in this case skewness is 0. Why? Because this numerator is 0. So 0 divided by anything is 0. So one very important point to note that is, since skewness for this data is 0, using this information the skewness is calculated value of skewness is 0. So this means that the distribution is symmetric. So another measure of skewness mostly used is by using the movement ratios denoted by square root of first movement ratio beta 1, square root of beta 1. So square root of beta 1, and note that beta 1 it was summation z cube whole square. So if we take square root, so it means this square will be cancelled with this, so we are left with 1 over n into summation z cube, where I ranges from 1 to n. So this is the skewness. It is square root of first movement ratio, and note that this z is a standardized variable, so we can replace it with its origin with its value x minus mu over sigma and whole cube as it is. So if we are dealing with population data, we have to use this mu and sigma. Mu is the population mean, sigma is the standard deviation in case of population data, and if we are using the sample data, we have to use x bar and small s. So we can use this big S as well. So we have studied in case of when we discuss the standard deviation topic, that small s for unbiased standard deviation and big S for the biased one. You can use any of these two. So x minus x bar is the sample mean and s is the sample standard deviation, and we have to replace this beta 1 by b1, square root of b1 as well. So remember that for symmetric distributions, the value of skewness is 0, and the value is it takes positive value for positively skewed distribution, and it takes negative value for the negatively skewed distributions. So it means using this formula we can calculate skewness, and we can tell whether our distribution is positively skewed. If the value is positive, it means positively skewed, and if it is negative, negatively skewed. If it is 0, we will say that the distribution is symmetric. So this is one very important formula. So before moving ahead, I am going to use this formula to calculate skewness using Microsoft Excel. So here is the data in Microsoft Excel. I have just taken hypothetical data. So this data is, I have labeled this data as X, and it contains 16 observations. So first observation is 27, next 33, and it goes up to 38. So I have labeled it as X. So first we can use the average built-in function to calculate the mean value or the average value. So using the average function equals average b5 to b20, we can calculate mean, and we can also calculate the standard deviation using Excel built-in function. So in order to calculate standard deviation, so let me calculate here. So in order to calculate standard deviation, we can use STDEV formula. STDEV is a built-in function which is used to calculate standard deviation. So and next we are interested in provide the suitable cell range B5 to B20. So this will calculate the standard deviation of these numbers. But there is one very important point which should be noted, that this formula STDEV, it is used it uses the formula summation x minus x bar whole square divided by n minus 1 instead of n. So it means it gives us the unbiased result. But currently we have been discussing that in order to calculate the standard deviation, we should use we have used n. So in order to calculate standard deviation using n, we have to adjust this formula by using one simple trick. So if we press enter, so this is the standard deviations. So it is obtained by summation x minus x bar. So it means calculating subtracting this mean, which is 27, from each x values, then square of the deviations, and then sum divided by n minus 1. But if you want to divide these observations with n, so in order to calculate it, you need to add this mean as well. So now this denominator will be n minus 1. So currently the number of observations in this data are 16 plus this one additional observation, which is the mean value, so 17. So 17 minus 1, we get 16. So there are 16 observations in our data, so it means we have added this additional observation, which is the mean. So it means now the denominator becomes 16, which is which is same as the total number of observations in our data. And we also know that if we subtract this mean x minus x bar, so x minus x bar is this sum is 0, so that's why this 27 minus 27, so it will be 0. So it means this new observation which I have added, it will not make a big difference in the sum. So because we are adding 0 and but we are adjusting the denominator. So this stdev command is very important, but remember that while calculating standard deviation using this built-in function stdev, we need to add the mean in the reference cell as well. So press enter. So this is the standard deviations. So I have calculated the mean and the standard deviation. So okay, so now look at this formula. So I have x bar in hand as well as this s in hand. So here this is x bar, which is 27, this is standard deviation, which is s. So I am going to delete all these entries, I am going to recalculate it. So using this formula, look at this formula. So formula for skewness is we have to subtract x bar from each x values, and then we have to divide this difference with the standard deviations, and in the end we have to take cube. So before taking cube, first I am going to calculate the standardized variable. So let us define a standardized variable, which is z. So it is actually what? It is x minus x bar, our sigma. So this is x minus x bar. X bar is this one. So note that you need to put dollars because we have to fix this entry. So x minus x bar divided by sigma. So sigma is this one, and we need to fix it as well using the dollar signs. So this is how we can calculate this standardized variable. So just subtract the sample mean from each observations and divide this difference by the standard deviation. So press enter. So this is x minus x bar. I'm going to adjust the width of this cell so you can copy it down throughout. So you can see that this is x minus x bar, our sigma. So once you have the standard deviation, the standardized variable in hand, so using this formula we have the z variable. So now take its cube and then take sum divided by n, you will get the skewness. So in order to take cube, so z cube, so it is the cube of this entry, so c5 raised to power 3. So copy it down throughout. So in the end we need to take sum divided by n, or in other words we can calculate directly the average. So average of all these entries. So it is average of D5 to D20. So this will give us the square root of beta B1, or it is actually the skewness. So press enter. So here we get 0.29. So since 0.29 it is close to 0, or you can say that actually if skewness is close to 0, it means the distribution is symmetric. If it is positive, it means it is positively skewed. Positively skewed means right tail is longer than the left tail. If it is negative number, it means the distribution is negatively skewed. and graphically we can say that left tail is longer than the right tail. So here, as far as this number is concerned, we have 0.29. So we need to check whether it is actually different from 0 or it is by chance different from 0. So if it is as far as this number is concerned, 0.29, so we can say that there is a slightly the distribution of this data set is slightly positively skewed. So this is how we can use Microsoft Excel to calculate skewness. So now let us discuss the concept of kurtosis. So Carl Pearson introduced the term kurtosis, literally the amount of hump for the degree of peakedness or flatness of a unimodal frequency curve. So when the peak of a curve becomes relatively high, then that curve is called leptokurtic. So here you can see that this green one, it is relatively high as compared to this middle curve, which is benchmark, and this middle curve is you can say it is curve of actual normal distribution curve. So we have to compare each curve with this benchmark curve. So if the peak of a curve becomes relatively higher than the normal curve, then it is called leptokurtic. It has a special name. These are the just fancy names. So when the curve is flat topped, then it is called platykurtic, this third one. So you can see that here at the top it is comparatively a flat curve, so it is the platykurtic. So since the normal curve is neither very peaked nor very flat topped, so it is taken as a basis for the comparison. So this middle one, it is actually the normal curve, so it is called the mesokurtic. So leptokurtic for the curve having peak higher than the normal curve, and platykurtic is the curve having peak lower than the normal curve, and meso is the curve having peak matching with the peak of the normal curve. So mesokurtic is our basis for the comparison. We take it as our basis, so we can so we take it as the benchmark curve. So we compare all the curves with this mesokurtic curve, which is the curve for a normal distribution. So kurtosis is usually measured by the movement ratios, which is beta 2, the second movement ratio, and for population data it is cult. We can use cult as well. So it is beta 2, which is 1 over n into summation z raised to power 4, where I ranges from 1 to n. Or we can replace this z by its value xi minus mu over sigma raised to power 4. So for sample data we have to replace these population movements with the sample movements. So x bar and s will be used, and instead of beta 2 we will use b2. And for normal distribution the value of kurtosis is 3. So when it is greater than 3, then the curve is more sharply peaked, or it is called leptokurtic, and has narrower tail than the normal curve, and it is leptokurtic. When it is the value of kurtosis is less than 3, the curve has a flatter top and relatively wider tails than the normal curve, and it is said to be platykurtic. So we can use these formula to calculate the kurtosis in Microsoft Excel. So here is the same data set in our Microsoft Excel spreadsheet program. So here is the formula for calculating curt. So curt is B2, which is 1 over n into summation z raised to power 4, or we can replace this z by x minus x bar over sigma, our s, which is the sample standard deviations, x bar is the sample mean. So just we have already calculated this z, so it means we need to calculate z raised to power 4. So it means C5, then this caret sign, the power sign, cap sign, and then 4. Then copy this formula downward, and then take the average of all these values. So average, it is average of E5 to E20. So this is sum of Z4 divided by N, so it will give us the average. We can use the average function to calculate this expression, which will be kurtosis. So press enter. So here it is 1.69. So now we know that if calculated value of kurtosis is exactly 3, or it is very close to 3, then it means this is a normal curve. So but if it is greater than 3, then we get leptokurtic. If it is less than 3, we get platykurtic. So here its value is 1.69, which is less than 3, so we can say that this data point, it is showing us the platykurtic behavior. So it is not normally distributed. So mean is different from 0, also kurtosis is different from 3. Skewness is different from 0, and kurtosis is different from 3. So we can say that this distribution, these data points, 16 data points, they are not normally distributed, or they are their shape will not be like the normal curve. So now we discuss another important concept which is related to kurtosis, is the excess kurtosis. So we can use EK to denote excess kurtosis, E for excess, K for kurtosis, and it is defined as excess kurtosis is the kurtosis minus 3. So we know that for normal distribution the value of kurtosis is 3, so that is why the new formula, the new definition, which is excess kurtosis, it is kurtosis minus 3. So for normal distribution, excess kurtosis is 3 minus 3, so value of excess kurtosis is 0. And when kurtosis is greater than 0, so it means when kurtosis is greater than 3, so we have suppose 4, value of kurtosis 4, so 4 minus 3, we will get excess kurtosis greater than 0. So when excess kurtosis greater than 0, then the curve is said to be leptokurtic, and when excess kurtosis is less than 0, mean this kurtosis is less than 3, so then the curve is said to be platykurtic. So here in the diagram, so when we get excess kurtosis positive, it is leptokurtic, and when it is 0, we will get mesokurtic or normal distribution, normal curve, and when it is negative, we get platykurtic. So this is one very important concept, so which we can use in order to calculate this kurtosis. So another measure of kurtosis known as percentile coefficient of kurtosis. It is defined as kurt is equal to QD divided by P90 minus P10, where QD is the semi-interquartile range, or also called quartile deviation, and it is equal to Q3 minus Q1 whole divided by 2, and P90 is the 90th percentile, P10 is the 10th percentile. So for any given data set, we can calculate Q3, Q1, P90, P10, and we can calculate this kurtosis using this result. So this is all about kurtosis. So now let us review the main concepts which we have discussed in today's lecture. So in today's lecture we have discussed the relationship between central movements and the movements about origin, and we also we have discussed the movement ratios beta 1 and beta 2, and the concept of skewness and kurtosis. So in the next lecture we will discuss how we can describe a frequency distribution using different movements, skewness and kurtosis, and then we will introduce you to the probability, and in the probability section we will provide some basic definitions and basic concepts related to probability. So till then, Allah Hafiz.